Hello, this is Ferhat Tigrek. In this screencast, I will introduce the likelihood function, which is the foundation of the Kramer rollover bound, maximum likelihood estimation, and name and person binary hypothesis testing. Likelihood function itself is a very simple twist on the probability density function. Yet, the tools derived from it are powerful and allows us to solve a wide variety of problems. To discover how the likelihood function works, first we need to appreciate the stochastic nature of our data. Our starting point is the assumption that our data is generated by a deterministic source with additive noise. The way we formulate this assumption is as follows. We have the data sample xn, which is equal to the sum of the output of the deterministic source, the signal model Sn theta, and the noise sample omega n. The deterministic source is controlled by the parameter vector theta, which consists of the deterministic but unknown parameters. But this formulation considers only one data sample. Let us think about a data set. A data vector x that consists of capital N such samples is generated by the signal model vector S with additive noise vector W. Now, if the signal model is deterministic, where is the randomness of the data coming from? The stochastic part is coming from the noise. Let's focus on the noise. It's a random process, which means each noise sample is a random variable. We have no way to know what the value of a sample will be before we actually sample it. Once we sample it, the noise sample becomes an observation. But even before sampling, we are not totally uninformed. We have probability values associated with all the possible outcomes of the sampling. In other words, we have a noise model in terms of a probability density function. The noise example you see on the left-hand side is generated by drawing samples from a normal distribution with zero mean and variance equal to 1. The probability density function for a noise sample is plotted on the right-hand side. At this point, we can return back to our data. The stochastic nature of our data is the result of the additive noise. So, we can say that the deviation of our data from the deterministic but unknown signal model is due to the additive noise. This deviation is a stochastic process that is governed by the distribution of the noise. So, based on this distribution, we can talk about the probability density function for our data. If the deviation of the data from the model is governed by the distribution of the noise, then the data itself is a stochastic process with a distribution that depends on the controlling parameter theta. Now we are ready to define the likelihood function. As it turns out, the probability density function for the difference between the data and the model is a function of both the controlling parameters theta and the data vector x. And remember, the probability density function concerns the outcomes of an experiment. Now, after we sample the data, we are no longer dealing with the possible outcomes and their probabilities. The data is there. The observations become a fact instead of a probability. So, let's put the observation vector back into the probability density function. Sure, we will get a value out of that probability density function. But now that the data x is not a variable anymore, we have a function of theta alone. That is the likelihood function. As the name implies, this function gives the likelihood of getting the data x that we observed for different values of the variable theta. At this point, please note that the plot on the likelihood on the right-hand side still concerns a single sample. So, if we are given a single sample, we can calculate the likelihood of our data for different values of theta according to the plot on the right-hand side. For the data vector, we consider the joint probability of sampling all the data points at hand. This means the probability density function for the data vector is obtained by multiplying the probability density functions for individual samples. Therefore, the likelihood value for the data vector is also obtained by multiplying the likelihood values for individual samples. At this point, It becomes clear that for large data vectors, we have to deal with extremely small numbers when calculating the likelihood functions. To avoid that, and also to avoid large multiplications, we introduce the log likelihood function. Quite straightforward. We take the natural logarithm of the likelihood function. We will see that this natural logarithm is extremely convenient when dealing with exponential distributions. But that is for later. Let's now focus on the animated figure on the slide. On the left-hand side, you see the data samples we collect. The data is generated by 1 volts DC plus white Gaussian noise with zero mean and variance sigma squared equal to 1. In the middle, we have the log likelihood functions for each individual sample. Consider this. If we had only one sample, x1, at hand and asked to estimate the voltage value, how would we come up with an answer? There's no way to predict the noise, so we might as well just give the reading we have for that sample as the voltage level. But we can say this. The value of x1 is more likely if the value of theta is equal to x1, given the noise is Gaussian distributed. Now, we collect another sample. We can operate the same reasoning for x2 and end up with another likelihood function. The middle figure shows the likelihood functions for each individual sample. However, we can also ask ourselves this. What is the likelihood of getting x1 and x2? And we can keep collecting more data samples and ask the same question again. What is the likelihood of getting the data vector x that contains capital N samples? The answer is depicted on the right-hand side figure. For convenience, theta is equal to 1 is marked on the figure. You can observe how the likelihood function sharpens and the peak converges to theta equal to 1. This figure shows the principle of the maximum likelihood estimator, which gives the peak of the likelihood function as the estimate for the parameter theta. You can find more on the maximum likelihood estimator in the lecture notes. With this slide, we conclude the screencast on the likelihood function. I hope you enjoyed this simple yet powerful tool in our estimation toolbox. If you have questions about this screencast, please contact us. Also, don't forget to check the MATLAB live script on the likelihood function. Have a nice day.